So our last topic, and this one actually depends upon how algebraically talented you are, I guess. The last topic that we have is something called implicit differentiation, and I want to at least introduce it today and let you have a chance to practice it, so that when we talk on Tuesday that I'll have a chance to know how you've done. So let's talk about implicit differentiation. Get the calculator out of the way because we're not going to need it for... This is the one where the calculator isn't going to help you. You've got to do this one on your own. Explicit functions versus implicit functions. Most of the functions that we have dealt with in this class, most of the functions that you dealt with in 1630, are called explicit functions. Explicit functions are where there are two variables and one variable can be set on one side and the rest of it is put in function notation, so that you have y or f of x on one side and then the expression x on the other side. So explicit functions are functions like this linear equation, that quadratic equation, that cubic equation, logarithmic equations, exponential equations, rational equations. Those are all explicit functions. They can be solved for one of the variables. Implicit functions, we can't do that. This is still an explicit function, even though it looks like everything's all mixed up. It's still an explicit function because we can solve that equation for y by moving the -3 over to the other side with 6 and have 3x plus 6, and then divide both sides by the 4x and have y by itself. So y is an explicit function dependent upon what the value of x is. Okay? So these are explicit functions. I'm showing you this one because I don't want you to think just because you see x and y in the same term automatically means you've got an implicit function, although that is going to be something you look for. So what about implicit functions? Implicit functions are functions that you can't readily solve the equation for y. You can try, but you're going to run into problems. And here's the first example. Y squared plus 2yx plus 4x squared equals 0. You can't solve that for y. There's nothing you can do because it shows up in both terms. It just won't work, and you're not allowed to divide by the variable on both sides. So this is still an implicit function. It's not implicit just because y shows up here, but because y shows up in a separate term. It's in two separate terms. Same thing is true here. You've got y's in that term, and that term, and that term. The y's are all mixed up with the x's. They're all multiplying times the x's. So you can't solve that equation for y, which means taking its derivative, since we have to have an explicit function to take a derivative, we can't take the derivative quite as straightforwardly as we could otherwise. Now we can still take it, but it requires a little bit of algebraic manipulation. So what we're going to do is we're going to do something called implicit differentiation. So let's talk about what implicit differentiation is and how do you do it. So here is an implicit function. The first thing you need to remember is that when you take the derivative of y, y is a function of x, which means it's going to be chain rule. Okay? Y is a function of x, so it's a chain rule. This is a product. This is 3x times a function of x. Because y is a function of x. Plus 4 times some function of x squared. And that's equal to 10. So here's how we're going to do this problem. And I'll probably switch notation in a minute, but right now I want to make it really obvious to you that y is f of x. Okay? So what we have here is we have 3x and we need to do the product rule with this. So in order to do the product rule, we need two derivatives. We need the derivative of 3x. What is the derivative of 3x? Okay. We need the derivative of a function of x. What do we usually call that? Without any idea what it actually is. F prime of x. Is f prime of x the same thing as y prime? Yes. That's going to be a key right there. So when we do the chain rule part, or excuse me, the product rule part of this, we're going to take first times derivative of the second. And I'm going to use y prime to talk about the derivative. Plus the second, which is f of x, or y, times the derivative of the first term, which is 3. So there's the derivative of your first term, 3xy. The derivative of 3xy is 3xy prime plus 3y. And now we're going to add the derivative of 4 times some function squared. This is chain rule. Chain rule says bring the 2 down in front and multiply it times the 4. That gives us 8. Times the function inside the parentheses. Reduce the power by 1, and that function is to the first power. And then the last thing we have to do is we have to take the derivative of f of x, which is y prime, just because that's the easiest way to write it. Okay? Now that function is just whatever was inside the parentheses. We can switch back to y at this point. These y's are still f of x's. What's the derivative of 0? I'm sorry, of 10. It is 0. Now here's how if you can get through this step, the rest of it is really not hard at all. What we want is we want all of the terms that have y primes on one side and all of the terms that don't have y primes on the other side. Okay? That's our goal. Our goal is to move this and that to the other side. and get this by and it'll leave this by itself essentially. Now we can either leave both of these over here and move that, or we can move both of those over there and leave this here. It actually, to me, is easier since I only have to move one thing. It's easier to me to subtract 3y from both sides. So what I have now is 3x y prime plus 8y y prime is equal to, subtract 3y from both sides, 3y. It's probably not your favorite thing to do, but can you factor this? Can you factor out a greatest common factor? It'd be y prime. That's why we wanted all the y primes on one side. So now it's no trouble at all to do this. And we have our derivative. Okay? It's just another way to take derivatives. The key to remembering how to do this is every time you see a y, think, okay, that y is a function, therefore it has a derivative. So you take its derivative by calling it y prime. And then other than that, you treat it just like you would any other expression. So let's try another one. Now, the textbook uses the terminology dy over dx. I avoid that because I know, I see the look on your face every time I put a fraction in here. I know how much you love fractions. So that's why I tend to go with the terminology dy dx is equal to y prime, because y prime doesn't look like a fraction. Even though it is a rate of change, it doesn't look like a fraction. So this is your process, and we just need to practice. Let's practice a couple more, and then I'll send you out of here to practice on your own. Find the derivative of this function. We're going to take the derivative of every single term, but before we take the derivative of every single term, I'm going to change this to x to the 1/2 power. And I'm going to change this to y to the 1/2 power. Okay? Because we don't have a rule to deal with roots. What's the derivative of x? 1. This is a product. It's a multiplication problem. So that means we need to take x to the 1/2 and multiply it times the derivative of y to the 1/2. And that's going to be 1/2 y to the negative 1/2. And then anytime you take a derivative of a term with y in it, you also add on y prime. Plus y to the 1/2 times the derivative of x to the 1/2. What's the derivative of x to the 1/2? Bring power down in front, multiply by x, reduce the power by 1. And then on the other side, on the equal sign, we have y squared. So you bring the power down in front, 2y to the 2 minus 1 is 1, 2y to the first, and chain rule says you have to multiply that by y prime. So now what we've got is 1 plus 1/2 times x to the 1/2 power y to the negative 1/2 power plus 1/2 times y to the 1/2 power times x to the negative 1/2 power is equal, see, I left out a y prime here, is equal to 2y prime. And to make it easier to keep up with, what I usually do is I take a highlighter and go through and mark all my y prime terms so I know what I'm trying to get together. So that means that I need to get this term over here with this one, or else I need to move everything else over. It doesn't matter which way you go, but since this is the only one that needs to move over here, I'm going to move it. One plus, and I'm going to move this whole term. And since it's added, I'm going to subtract it. And then I'm going to keep this one over here. And then I need to factor out my y primes. So I have 2y minus 1/2 x to the 1/2 y to the negative 1/2. And I'm going to divide both sides by that. So when I've divided off both sides, it's no longer there, and that means what I have here is y prime. Now, it's not pretty. I could put the roots back in, and that might make it a little prettier, but it isn't going to help too much with that unless I drop it into a denominator and have uglier fractions than I've already got. So this works fine if you leave it as powers. Okay? If you're going to put it in Pearson, be sure that you have parentheses around your numerator and denominator. Or if you're going to put it in your calculator for any reason. But since Pearson has the fraction bars, it's easy enough to do it with the fraction bars and the powers. Okay? Now, if you can do that one, you can do just about any of them, because this one, it's not that it's hard, but those 1/2 powers get tricky. Okay? Katie's looking at it going, oh my God. Okay, this is the only examples that I printed off. So we've got this one left, and then I will spend some time with you next time taking questions on the ones in my math lab, if you need help. The demand function for a certain commodity is given by this. P is the price in dollars and Q is the demand in hundreds of units. Find the rate of change of demand with respect to price when Q is equal to 100. And notice that it says find dQ over dP. That means this needs to be solved for Q. Which is tricky. Put this up so I don't lose it. So I'll let y'all think about that for a minute. Can you solve that for Q? I'm betting you can. Because your Q's showing up here in two different terms. So you really can't. You're going to have to use implicit differentiation on this one, because I'm not asking you to find P prime. I'm asking you to find Q prime. So we do have to use implicit differentiation. We can do this. Stick with me. Get another piece of paper though, because we need a little more room. Since we're finding the derivative with respect to P, P is the independent variable. What's the derivative of P? Let me change things around and make it a little easier for you. P is X. Q is Y. So our function is X equals 500,000 over 2y cubed plus 400y plus 5,000. X is the price. What's the derivative of X? 1. This is a function of X. We need its derivative. It would be easier to take its derivative and for you to think about taking its derivative if I write it like this. Because otherwise what we're going to be doing is we're going to be having to apply the quotient rule, and part of it's going to disappear anyway because the derivative of the numerator is 0. So it'd be just as easy to go ahead and move the denominator up to the numerator and apply chain rule instead. Okay? So -1 times 500,000 times that to the -2 power times the derivative of that. So what we're going to have then is going to be 1 is equal to -500,000 times that original expression in parentheses to the -2, and I'm not even leaving enough room to put it back in there. And now I need to take the derivative of that function. So the derivative of 2y cubed is 3 times 2 is 6y squared y prime plus 400, and the derivative of y is y prime, and the derivative of 5,000 is 0. So that means 1 is equal to negative 5,000, I'm sorry, 500,000. Those zeros do make a difference. I'm going to move this into the denominator just because it's easier than keeping track, it's easier to keep track of it. So all I did really was I put it back down there and it's squared times everything that has a y prime in it. And I want this over here. And since this is negative, then this is going to be positive. Whoa. Sorry. That's going to be 1 divided by, not plus, because this is a product. Now, since this is 1 divided by that, it's the same thing as 1 multiplied by the reciprocal of that. So flip it upside down. And then on this side, I'm going to factor out the y primes.
Get rid of this square.
No, you don't. Thanks, Kate. Stop writing too soon. So we took the derivative, divided both sides by this factor, which means we flipped that factor over and multiplied by it, and since we multiplied by 1, it didn't change. Then we factored out y prime on the other side. Now we need to divide both sides by 6y squared plus 400. And rather than divide by it, I'm going to multiply by 1 over that, because that's easier to keep up with. Ah. Thank you. So this is actually your derivative And the only thing that I'm going to do to make that look any different is instead of just doing this, I'm actually gonna move this over here with the negative 500,000 in the denominator. That way I don't have that extra term. So here's your derivative after all that. Now, I'm sure you can see that implicit differentiation can be very ugly. It's very tedious, but unfortunately there's no way around. If you've got a function that has x's and y's mixed up in it, it's an implicit function. This is the only way to get your derivatives, okay? Now, we've got the derivative. At this point, all we need to do is plug in, let's see, where's my original problem again? Find the rate of change of demand with respect to price when Q is 100. So all we would do then, since Y was Q, is everywhere we see a Y, we plug in 100. And what you're going to find out is that at Y is equal to 100, the derivative, Y prime, is negative 138. And actually, Q is in hundreds. That's actually 10,000 because that's 100 hundreds. And demand is decreasing at the rate of 13900 or 13,900 units per dollar. And it's 138 point something. I think it would round to 139. So when the demand is 10,000, then the demand is decreasing at the rate of let's say about $139,000 per dollar change, or units per dollar change in price. Okay? Anyone have any questions or anything else you need to remind me of, bring up? Okay, let's get Shelby caught up and try to do a little bit of review before we go on Tuesday next week. Okay?
So it says all of the new Wednesday, is that not test on Thursday?
That was when I was originally planning to give you a test on Thursday, but I don't think I'm gonna give you a separate test over this.
Wait, what?
I said originally I had planned on the test over this to be next Thursday, but I changed my mind and decided just to include everything on one last test rather than try to give you two more. Because you've got a lot to do at this point too.
Well, I thought we only had 4 tests anyway, like including the exam. I think that's what like the rubric said, it's like 4 tests, including the exam.
Yeah, and I broke it up different this time than what I normally do. Normally